Hey guys, this video covers Chapter 7, Section 3 on our sum and difference trig identities. So what I want you to do is sketch a unit circle. It doesn't have to be perfect or beautiful, just sketch a unit circle. In fact, you really only need the first and second quadrants. We're not even going to deal with the bottom hemisphere at all. And what I want you to do is draw two angles. So if an angle starts in standard position over here at 0, I want you to put one of those angles in the second quadrant, or one of those terminal sides in the second quadrant, and call it angle alpha. And I want you to draw a second ray, which will be a second terminal angle for a different angle, somewhere in the first quadrant, and call its opening angle beta. So we have angle alpha, angle beta. Okay, the next thing I want you to think about is how can we write these coordinate points? So like if I wanted to figure out where this red coordinate is on the unit circle, we need to remember that all of the coordinates, x and y, by definition of what we know about the unit circle, can be rewritten using a trig ratio. So we know that sines of any angle theta on the unit circle represent y values, and we know that our x values can be written as cosines, which means if I want a coordinate points for this red point, again, these are not on the unit circle. These represent, it's on the unit circle, but it's not like the typical one. So this is not square root of 2 over 2 or square root of 3 over 2. This just represents any coordinate point. Instead of writing its coordinates as x and y, I can write its coordinates using cosines and sines. So I could write this coordinate using cosine of beta, and then its y coordinate being sine of beta. And I could do the same for the blue coordinates. Instead of calling it x and y, I know x's can be written as a cosine, so this one would be cosine of alpha times the sine, or not times, comma, the sine of alpha. So that's its x and y coordinates. I apologize for my sniffles. Okay, while you are writing that, I want to remind you of, just that proofs are not meant to make your life miserable, even though they make us miserable sometimes. Mathematicians did not come up with them just because. Everything we do in math is done because somebody proved that it worked in every single case, and that allows us to use those operations, or to use that particular identity. So what I want to do is I want to use our knowledge of the law of cosines and the distance formula to derive one of our sum identities. Okay, now what I want to do first before we write that out is make a triangle. So if I connect my red and blue coordinates, I have created a triangle. And for that triangle, so as we don't confuse alpha and beta and A's and B's and C's and stuff, I just want to label my triangle with just random variables. Let's call the top one P. Let's call the blue side Q and the red side T. So I want to use the law of cosines and the distance formula to represent the length of P. So the deal is, if this is a unit circle, we know that Q and T are both radii of the circle, so they're both equal to 1. Okay, but the thing is, I don't know what P is. I don't know how to express that. So if you remember, the law of cosines, we used it a couple of chapters ago, is C squared equals A squared plus B squared minus 2AB times the cosine of C. Now, there are 3 versions. This is just one version. Okay, but instead of A's, B's, and C's, I have P's, Q's, and T's. So we're going to substitute in what we know using our triangle. Okay, C is the length that we're solving for, though. So in that case, that is our P. So P will be C. So that will be P squared equals A squared plus B squared. Well, my other 2 lengths, I already know are 1, right? A and B represent Q and T. So if this is A and this is B, because those are radii of the circle, we know that those are 1. So that'll be 1 squared plus 1 squared. Minus 2AB, again, we know that's going to be 2 times 1 times 1, is the cosine of C. Now we know C is P. I'm going to put P there. And then I want to simplify this even more. We know 1 squared plus 1 squared is 2, minus 2 times 1 times 1 is still 2, times the cosine of. Now the thing with P is that doesn't really make sense, right? On every unit circle, P isn't defined. But angles like alpha and beta, we know what those are. Or we can find what angles are. So I want to represent angle P in terms of alpha and beta. Now, if this is side P, angle P is the angle opposite of that. So if I want to represent angle P in terms of alpha and beta, then angle P would simply just be alpha minus beta. So it doesn't look like you did much, but you did. There's nothing more we can simplify. So we're just going to let this expression or this equation hang out here for a second. And then I want to use what we know about the distance formula to, instead of using trig to find the length of P, let's use the distance formula. Now, if you recall from your geometry days, distance formula is square root of x2 minus x1 squared plus y2 minus y1 squared. Now, the x1s and the x2s just come from your coordinates. So I'm trying to find the distance between my red and blue coordinates. So if I'm going to plug in x1s and x2s, all that's doing is basically determining which coordinate is your first coordinate, which coordinate is your second coordinate. So perhaps we'll say that cosine, or that this red coordinate over here, we'll call that our first one. So this will be x1, y1, and over here will be x2, y2. So if I'm trying to find the distance, I need to use these 4 numbers inside of the distance formula. All right, so if I continue, then D, remember I'm using distance to find P, so that's going to be P equals the square root of. Now, x2 minus x1, well, x2 is my second x coordinate, so that's going to be cosine of alpha minus x1, we said will be the cosine of beta, squared, plus y2 minus y1. So y2 will be the sine of alpha, minus y1 is the sine of beta, squared. So all that's under a radical. Now that radical is going to be a little annoying. So we can get rid of the radical if we square both sides, right? So if we square both sides, we put p squared equals, on the right-hand side, the radical goes away. So then we just have cosine of alpha minus cosine of beta squared plus sine alpha minus sine beta squared. Now, the goal is to kind of clean this up a little bit as well. So what I want to do is I actually want to square out these binomials. Now, some of you might be able to square these terms in your head. Some of you may need to see it written like this. Cosine alpha minus cosine beta squared means cosine alpha minus cosine beta times itself. Right? So when you FOIL that, many people forget that term that is in the middle. Plus, if you need to write out the full square on this side as well. Sine alpha minus sine beta times sine alpha minus sine beta. Again, this looks like a hot mess, but some of it's going to start to combine here in a second. So then if I have p squared equals, I want to FOIL, and I color-coded it, I want to FOIL the green stuff. So first, outer, inner, last. So if I distribute that, my first term, cosine alpha times cosine alpha, is cosine squared alpha. So there's the first term. My inner and my outer terms are the same, but with a minus sign. So that'll be negative 2 cosine beta cosine alpha. And then the last negative cosine beta times negative cosine beta will be positive cosine squared beta. Temporarily it looks worse. Then if I FOIL the blue stuff with the signs, I'm going to get basically the same exact thing as I did earlier, but with signs and alpha and beta as well. So it'll be sine squared alpha minus 2 sine beta sine alpha plus sine squared beta. Now, you cannot cancel things that don't have the same angles. Okay, so like, you can't cancel if it said sine squared alpha minus sine squared beta. Those can't cancel because they're not exactly the same. However, what you can do is hopefully sine squared and cosine squared things make you think about your Pythagorean trig identity. So if we group those together, so let me do sine squared alpha plus cosine squared alpha, we know that that's going to equal to 1. Okay, plus, let me just continue to re-scramble my terms here. Sine squared beta plus cosine squared beta, I know that will also equal to 1 using my Pythagorean identity. And then if you look at the two terms that you have left, so let me use a different color. This blue term here and this one here, negative 2 cosine beta cosine alpha, negative 2 sine beta sine alpha, I can factor out a negative 2. So let me do that. If I factor out a negative 2 from each of them, then I'm left with, in this one, I'm left with cosine beta cosine alpha. And in my second term, I'm left with plus sine beta sine alpha. Again, it looks like a hot mess, but look how lovely this is. In my next step, I know, so I have p squared equals, I know sine squared alpha plus cosine squared alpha is 1, and I know sine squared beta plus cosine squared beta is 1. And actually, to save us from having to write all of that again, if we just use that we know those simplify to be 1, then I have p squared equals 1 plus 1 is 2 minus 2, and then all that yucky stuff, cosine beta, cosine alpha, plus sine beta, sine alpha. And that's as far as we're going to go for this one. Now you're like, Miss Chandra, why the heck did we just do that? That kind of racked my brain. I don't understand. You kind of went fast. I didn't follow everything. That's okay. The main thing you need to know is I used distance formula. I got down to this thing here. I used law of cosines, got down to this thing here. So here's the deal. If p squared is equal to, I have p squared equals something and p squared equals something else. If both these equal p squared, then that means these things have to equal each other as well. So then, if we set them equal, then I get 2 minus 2 cosine of alpha minus beta. That was the law of cosines result. That should equal the p squared for the distance formula, 2 minus 2 cosine beta cosine alpha plus sine beta sine alpha. And then if I clean this up a little bit, if I subtract 2 from both sides, that disappears. And then if I divide both sides by negative 2, those negative 2's disappear, leaving me with cosine of alpha minus beta is equal to cosine of beta, cosine of alpha, plus sine beta, sine alpha. And you may not realize it, or you may not even appreciate it quite yet, but you just derived one of the sum trig identities, and that is super powerful. So on your orange sheet, what I need you to do is write the following. So on your orange reference sheet, we have 3 sum and difference identities. Here they are. The first one is sine. We're going to do sine. I'm not going to prove sine and tangent, but just know sine and tangent have them as well. So the first one is sine of alpha plus or minus beta. So it works for addition and subtraction. Instead of that, we could rewrite that as sine of alpha times the cosine of beta plus or minus cosine alpha times the sine of beta. Now, well, this one will kind of make sense to you. The next one might be a little confusing. It is the cosine of alpha plus or minus beta, and it's going to equal the cosine of alpha times the cosine of beta minus plus the sine of alpha times the sine of beta. Now, you may be confused at the symbols. What this means is, and you'll notice, actually, let's write the third one and then I'll explain the weird symbols. Tangent of alpha plus or minus beta is equal to the tangent of alpha plus or minus tangent of beta over 1 minus plus tangent alpha tangent beta. These are the 3 sum and difference trig identities to go on your reference sheet. Now, what you probably do want to make note of on your reference sheet is, notice sometimes I have plus minus, sometimes I have minus plus. Basically what that means is, throughout your whole problem, you will use, use either all top signs or all signs on the bottom. So either use all the signs on the top through one problem or all the signs on the bottom for another problem. So like for cosine, if I have cosine of alpha plus beta, since the plus sign is on top, then in my actual math on the right side, I will use the sign on top over here, which is a minus sign. Okay, so you will either follow all of the top signs or follow all of the bottom signs. All right, now let's show how these actually work. So the first thing I want to do is find the cosine of 105 degrees. Now, the thing to note is 105 degrees is not one of those easy angles on your unit circle, right? The easy angles on a unit circle are increments of 30 and 45 and 60 and 90 degrees. If they don't have, if they're not increments of those, they're a little bit more challenging to figure out. So what these formulas allow us to do, or these identities allow us to do, is instead of writing 105 as, or instead of trying to figure out 105, I can write it as a sum or a difference of 2 angles that I do know the numbers to. So I want you to think for a second. How else can I write the cosine of 105? What 2 numbers add or subtract to 105 that are increments of 30 and 45 and 60 and 90? And look, there are multiple options. Okay, when I did my notes originally, I used 150 minus 45, but you could also use one that'll probably be a little bit easier, is the cosine of 60 plus 45. Now, you should be looking at your unit circle as we do this, because that'll be easier. So what I've done now is I have the cosine of an angle plus an angle. So what if I call this angle alpha and this angle beta? Then you're going to follow the trig identity to expand it. So if I have cosine of alpha plus beta, plus is on the top, so I'm going to follow the top signs throughout. This can be rewritten as, so this is, I'm following this trig identity here. Alpha and beta, well, alpha will just always be your first number, beta will always be your second number. So now I'm going to have, instead of cosine alpha, we've claimed alpha is 60. So I'm going to have the cosine of 60 times the cosine of beta, which is the cosine of 45. Again, I have a plus sign, which was on top. So I'm going to follow the top sign on the right side, which is a minus sign. Sine of alpha, sine of beta. So it's going to be sine of alpha is 60 times the sine of beta is 45. From here, you should know these values from the unit circle. In the unit circle, cosine deals with x values, sines deal with y values. So at 60 degrees, my x value, that x coordinate at 60 degrees is 1/2. The x coordinate at 45 degrees is square root of 2 over 2. Minus the sine of 60, which is the y value at 60, is square root of 3 over 2. And the y value at 45 is square root of 2 over 2. And then all I have to do is simplify this madness. So we multiply fractions straight across. So these first couple will be square root of 2 over 2 times 2 is 4. Minus, then I can multiply these. Square root of 3 times square root of 2 using radical operations. This is just the square root of 6 over 2 times 2 is 4. Now, you cannot subtract radicals unless they have the same number on the inside. Okay, but I can just rewrite this since these fractions have the same denominator. I can just rewrite this as square root of 2 minus square root of 6 all over 4. Now, what this allowed you to do was not use a calculator at all to find the exact value of the cosine of 105 degrees by using the sines and cosines of values that you do know, like 45 and 60, from the unit circle. And that's it. That's how you would leave your answer. There's no more ways that we could simplify that. Let's do another one. What if I ask you for the sine of pi over 12? Pi over 12 is not on your unit circle. Now, if you're good with fractions, remember the goal is to try to write this as a sum or a difference of angles that you do know on the unit circle. If you're good at fractions, if your unit circle is in terms of fractions and you kind of understand them, you may know that pi over 12 can be the same thing as pi over 3 minus pi over 4. But what if you're terrible at fractions, or what if that just kind of confuses you and you don't understand what I just did? Well, you guys typically understand degrees a lot better than you do radians. So what you could do is you could just convert to degrees before you even start the problem. So if I want to convert to degrees, I'm going to take pi over 12. I'm going to multiply it by 180 over pi. So where my pi's cancel out. And 180 divided by 12 is 15. So instead of sine of pi over 12, I now can rewrite my problem as the sine of, I know I'm dealing now with 15 degrees. Now, 15 degrees is still not under unit circle, but can I write 15 degrees using two angles that I do know from my unit circle? So this is another one. When I originally did it, I used 60 minus 45, and you could use those two numbers, but you could also write it as the sine of 45 minus 30. And it doesn't matter which numbers you choose, as long as the numbers you choose are on the unit circle and they actually add or subtract to be the number on the inside. Now, I'm using sine this time. So I have the difference for my sine function. So I'm going to be using this identity, the top one. But the negative is on the bottom, so I'm going to be using minus on the bottom, and on the right side I'll be using the minus on the bottom as well. So you can be referencing this on your orange sheet. Okay, so the sine of 45 minus 30 can be expanded by doing, if alpha is 45 and beta is 30, then that means I'm going to have the sine of alpha, which is 45, times the cosine of beta, which is cosine of 30. Again, I'm using the signs on the bottom, so it'll be minus the cosine of alpha, which is the cosine of 45, times the sine of beta, which is the sine of 30. And again, using your unit circle, you should be able to tell me what all of these exact values are. The sine of 45 is the square root of 2 over 2. The cosine of 30 is the square root of 3 over 2. Minus the cosine of 45 is also square root of 2 over 2. And the sine of 30 is 1/2. And then I'll just do, regular arithmetic to simplify this. So I can multiply these fractions. That'll be the square root of 6 over 4. Minus, I can multiply these fractions and be the square root of 2 over 4. And now I have two fractions with common denominators. So even though I can't actually subtract square root of 6 minus square root of 2, I can just leave them separate like this, but both over 4. So you have found that the sine of pi over 12 is the square root of 6 minus the square root of 2, all over 4. Okay, let's do one more like this. Let's do tangents now. So what if I ask you for the tangent of 165 degrees? Okay, so again, my goal is to figure out how can I rewrite 165 degrees using angles that I know of on the unit circle. So I decided to use the tangent of 120 degrees plus 45 degrees. And I'm sure there are other combinations as well. So now I'm I'm going to use my tangent identity. Notice I have a plus sign, which is on the top. So I'm going to follow all of the top signs, okay, on the right side. So again, since I can't see both in screen, you should be looking at your reference sheet on your orange paper as we go through this. Okay, so I'm going to expand this. Remember, the first number is alpha, the second number is beta. So I have the tangent of alpha plus the tangent of beta. So that'll be the tangent of 120 plus the tangent of beta is 45. All over 1, I'm using the top signs, so that's going to be minus the tangent of alpha is 120 times the tangent of beta, which is 45. If I'm using my unit circle, tangent is a little bit different. You can't just grab x and y values. We have to remember that tangent is y over x. Okay, so like for this first one, if I'm trying to find the tangent of 120, I need to locate at 120 degrees, my y value is the square root of 3 over 2. My x value at 120 degrees is negative 1/2. Okay, and then we know that dividing stacked fractions like this is the same thing as taking the square root of 3 over 2 and multiplying by the reciprocal of 1/2, which will be, or negative 1/2, which will be negative 2 over 1. And then if I multiply straight across, these 2's actually cancel, and I'm left with negative square root of 3. So all of that was just to find the tangent of 120, which is negative square root of 3, plus the tangent of 45. I hope by now you know at 45 degrees is the square root of 2 over 2 over the square root of 2 over 2. The tangent of all of the 45-degree increments, the slope is always going to be 1, or negative 1 if you're in the second and fourth quadrants, over 1 minus, we already found the tangent of 120 to be square root of 3, times the tangent at 45 we already discussed is 1. So now I just got to simplify this. So let me kind of rearrange things. In my numerator, I'm just going to write 1 minus the square root of 3. And in my denominator, I'm going to have, I'm sorry, hold on. This is going to be in my denominator 1 minus the tangent of 120 was negative square root of 3. So I'm actually going to have a double negative in the denominator, which will make this 1 plus the square root of 3, right? Because that tangent was negative and the formula is to subtract. So 1 minus the negative will be positive. Now, in math, we are not allowed to have radicals on the denominator. So what I need to do is rationalize this. So you may recall from Algebra 2, I can rationalize this by multiplying by the conjugate, which is taking your denominator and changing the sign. So I can multiply by 1 minus the square root of 3 over 1 minus the square root of 3. And then I will multiply straight across. So that means in the numerator, sorry, y'all. In the numerator, I'm going to FOIL, right? This binomial times this binomial. And in the denominator, I'm going to FOIL. So carrying on. In the numerator, 1 times 1 is 1. Inner and outer, it's going to be negative square root of 3 minus the square root of 3, which will be minus 2 square roots of 3. Or if you want, I'll write it separate. So it'll be negative square root of 3 minus outer is the square root of 3. And then last, negative square root of 3 times negative square root of 3 is just going to be a positive 3. All over, if I FOIL the denominator, I get 1 plus the square root of 3 minus the square root of 3 minus 3. So then in the numerator, I get 1 plus 3 is 4 minus 2 square roots of 3. In the denominator, I get 1 minus 3, which is negative 2, and then 3, square root of 3 minus square root of 3 cancels. And then I can simplify one more time by dividing dividing everything by negative 2, essentially. And then I get negative 2 plus the square root of 3, right? So if I simplify by dividing everything by negative 2. So then we find that the tangent of 165 is equal to negative 2 plus the square root of 3. And that's as complicated as it gets. That was extremely lengthy, and I went through the algebra pretty quickly. But remember, you can pause the algebra. Okay, the very last thing to do is verification. So I apologize, I know this video is long. You may have needed to take a break, but we're almost done. These last two things are going to be pretty quick. So verifying is like proving. So I want you to verify that the cosine of pi over 2 plus theta is equal to negative sine theta. So this is a proof. Now, it's a little bit easier than the proofs that we've been doing because it just is. So what I want you to notice is the left side's more complicated, and it's already in the form of the sum of two angles using cosine. So what I want you to notice is if we use our cosine sum identity, right, and treat this as alpha and this as beta, then I can use that identity to expand the left side. So if I use that identity, that's going to be cosine of angle of alpha plus beta will be cosine alpha. So that's going to be cosine of pi over 2 times cosine beta, which is cosine of theta. And then because this is plus, that means I'm using the top signs. So that the top sign on the other side will be minus sine alpha times sine theta. So it's going to be sine of pi over 2 times sine of, or is it beta, which is theta. And then the right side, I'm just going to chill and keep the same as negative sine theta. Well, now you actually know some of these numbers. The cosine of pi over 2, if you're looking at your unit circle, cosine is the x value. The x value at pi over 2 is 0. So then I have 0 times the x value. We don't know this, right? We don't know what the heck cosine of theta is. Minus the sine value at pi over 2 is 1 times sine theta. And I want to know, I should be carrying my question mark symbol, sorry. Is that equal to negative sine theta? Well, 0 times cosine theta is 0. So that cancels. And then on the left side, all I'm left with is minus the sine theta, which means it is exactly equal to sine theta. So there's that proof. Okay, let's do one more proof. I want you to prove if the sine of a plus pi is equal to negative sine a. If you prefer dealing with thetas instead of like other variables for the angle, that's fine too. Okay, so again, I want you to notice the sine of alpha plus pi is written as the sum of two angles. So if you're looking at your orange reference sheet, if you're looking at the sum identity for sine, I can expand the left side of this equation. So if alpha is a and beta is pi, then the sine of alpha plus beta can be expanded by doing the sine of alpha times the cosine of beta. So that'll be the sine of a times the cosine of pi. I'm using the top signs, so it's going to be plus the cosine of alpha, so that'll be the cosine of a, times the sine of beta, which will be the sine of pi. And I want to know, is that equal to negative sine a? Well, again, I don't know what sine a is, so that's the input. But I do know that the cosine of pi, so my unit circle at pi, the x value is -1. Plus, I don't know what the cosine of a is, but I do know that the sine of pi, the y value at pi, is 0. So what that means is, if my cosine times 0 cancels, then I have proven that negative sine a is definitely equal to negative sine a. So that's how you can verify those proofs. You're going to use your identities to help you expand those angles that are being added or subtracted from each other. Again, I apologize for the length of this video, but that's how I had to fit everything in and not leave anything out. So I hope it helps.